Okay, we're on to exercise 13, and the question reads, calculate the percent dissociation of acetic acid, and they give you the Ka value for that. That's the acid dissociation constant, 1.8 times 10 to the minus 5 for each of the following solutions. So what we're looking here is a percent dissociation. Just remember what a percent of something would be. So let's say I have a class that has 30 students in it. And let's say 6 of those students got A's on a test. And I want to know what percent got A's. So that would be 6 out of 30 got A's. So it's the number that got A's out of the total number of students in the class. And if I do that little division problem and then multiply that by 100%, I'll get my percentage, which will be 20%. All right, so what the percent dissociation is going to be, let's take a reaction, the generic acid reaction. Get used to seeing this notation. It's HA. That means this is the proton and this is the conjugate base. This is the rest of it. And it breaks up into an H+. Again, if we're not including water in the reaction, it's just H+, not H3O+, plus the conjugate base. So that's just whatever is left after you've taken off that proton. Okay, when we wrote the equilibrium expression for this, it looked like this. That Ka, be sure I'm on screen here, is going to equal this times this, so the concentration of H plus times the concentration of A minus over the concentration before they dissolved of the entire acid molecule there, HA. Okay, so that's the equilibrium, that's the law of mass action, or the equilibrium expression for that. But to come back to my analogy, if you want to just know the percent dissociation, you take the number of hydronium only, not of this as well, not of the A minus as well, just of the H plus, divided by the total acid molecules you had at the beginning, and then multiply that by 100%, just like we did down here with students who got A's over total students. So it would look like this. This is percent dissociation. It's simply going to be H plus, the number that broke up, over the total number that we started with, times 100%. So it's not the same as computing the law of mass action for this. So we're going to use this. All right, so we still need to use an ice table. So write the reaction for acetic acid. Okay, and that's going to be CH3 and then the COOH, where this is the H that's going to dissociate. That's the proton that's going to break away. And that's a reversible reaction because it is weak. That means the H can go away, but it can also come back and reattach. That's not true with a strong acid. So that's going to give you the acetate ion. Negative because it lost a proton, plus the hydronium. Okay, so now just use that to create an ice table. So we have I, C, E, and this is going to start off with 1 molar for part A. So that's going to be 1. It's going to lose some number of moles X, and that's going to give you the equilibrium of 1 minus X. You're going to get to where you can do these ice tables really quickly if you practice. They don't have to be as slowly as I'm doing them. And then this we assume initial concentrations of 0. You add X. I hope this is starting to be repetitious for you because then that's when it starts to become easy. And there's X. So there's the equilibrium concentration of everything. Now, what we're going to do is we do have to figure out what that X is. So we do have to go ahead and use this equation. So it's going to be K, A, equals and it's going to be the acetate. And the hydronium over the acetic acid. Okay, when we plug in these values here, we end up with Ka, which we have as 1.8 times 10 to the minus 5. And that equals this times this, which is x times x. These two get substituted in there. X times x is x squared. And this one on the bottom is 1 minus x. And we're going to use our small variable assumption. So this goes away. We're going to assume x is very small compared to 1. Gone. So you just have a 1 on the bottom. So all you really have is x squared equals 1.8 times 10 to the negative 5. So you take the square root of both sides. And you end up with x equals so it's second x squared gives you the square root 1.8 times 10 caret negative 5 close parentheses, and it gives you this. So what is that? That is the concentration of H plus right there. That you substitute that in there, that tells you what the concentration of H plus is. Now we're not done with the problem. It wants to know the percent dissociation. So think of this. This is the number of students who got A's. And the 1 is the total number of students that we had in the class. So what we do is up here, we write percent dissociation is going to be 0.0042 over 1 times 100%. And when you do the math on that, you end up with 0.42%. Okay, so that's how you would do that one. I'm going to do the other one on a separate piece of paper because of the little bit crowded here. So I'll go ahead and bring that over here. And this time we're dealing with 0.1 molar instead of 1 molar. So it's done exactly the same way. So see if you can do it without looking at that example. See if you can do it on your own, okay? So it's 0.1 molar acetic acid. All right, so let's write the equation. Always write the equation and then just turn it into an ice table. So it's CH3, double arrows, and I'm kind of doing it kind of fast to show you how quick this works, how quick you'll be able to do these when you practice them, okay? Again, this is an entirely different problem from the last one, so we're starting 0 concentrations here. Okay, that's what we're trying to get. So again, we have K, write the law of mass action. All right, now we plug in our variables up here. Ka is 1.8. On the top we have x times x. This is the x for this. This is the x for this. So it's x times x, or x squared. Down on the bottom, it's the only difference is from the last one, it's 0.1 minus x. We're still going to assume that this is a very small amount compared to this. So this goes away. And so now you have just a little bit of a math problem. You got to multiply both sides by 0.1. Okay, this cancels with that, so you have x squared equals this, and do that on the calculator if you need to, or if you can see that it's going to be 0.18, you just slide the decimal over one place. Okay, and then you take the square root of both sides, and you end up with x equals second x squared gives you the square root 0.18 times 10 caret negative 5 close parenthesis, and it gives you this. Okay, now we want to do the same thing. We want the hydronium concentration over the concentration of the initial acetic acid concentration. Okay, and then you're going to multiply that by 100%. So what that gives us is, there's the hydronium ion concentration. Again, you take the X, you bring it back up here. That's the value there, and that value is the equilibrium. There's the equilibrium. It's the equilibrium value of the hydronium ion concentration. That's what you want. You know, what's the concentration of hydronium ions in your solution? So that is going to be 0.0013 over, and the initial concentration, be careful here, it wasn't 1, it was 0.1. 0.1 molar was the initial concentration. So it's 0.1, again, that's back up here, that number right there, times 100%. Okay, and if you do that, let's just do the math, let's do it one step at a time. This is going to give you 0.013 times 100%. And that, you're going to move the decimal over two places, or just do it on your calculator. You just multiply by 100. Don't hit the percent sign. Don't ever use the percent sign. Just multiply by 100 and then stick the percent sign on the end of your answer. So it's going to be 1.3%. And that's the percent that was dissociated. I actually find this a more useful number a lot of times than the equilibrium constant, but the equilibrium constant has a lot of uses in these problems. You know, it's saying that that only about 1% of the acetic acid ions or molecules break up into a hydronium and an acetate ion. So it's not a very big number. And for this, it was only 0.42%. So at a higher molarity, it's even a lower percentage that does it. Okay, that's kind of an interesting phenomena. Won't go into why that is, but it's very small percentage that actually break up when you have a weak acid. And how weak is it? It's moderately weak. It's a moderately weak acid. It's definitely not a strong acid, and it's not the weakest of acids, but it's 10 to the minus 5 there that I'm pointing at for the Ka. So not very many of those molecules break up. So you want to kind of take away little intuitive understandings like that of what these numbers mean. You're able to interpret these numbers and not just crunch numbers. Okay? Next problem for this acid. Okay, so we're on exercise 14, and it reads, lactic acid is a waste product that accumulates in muscle tissue during exertion, leading to pain and a feeling of fatigue. In a 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate the value of Ka for this acid. All right, so this again is a percent dissociation problem, except we're working backwards. They're giving us the percent dissociation. We have to work backwards and find K. So let's go ahead and write the equation. Okay, there it is. So we're going to set up an ice table here. And let's see what we can enter right now. And then we're going to have to make some calculations based on this percent dissociation. So what does that tell us? Well, the initial concentration of the solution is 0.1 molar. So that's going to, first of all, water is not involved. You can just cross that out. So this is going to be 0.1 molar. Everything up here is molar. And now we're going to have to do some calculations, because what we know is at the end of the reaction, it's 3.7% dissociated. So that's something that's going to be at the end of the reaction. That doesn't happen right at the beginning. That's at the end of the reaction. That means that's going to be an equilibrium situation. So let's go ahead and write. Let's go ahead and write the dissociation equation that we used in the previous problem. And what we said was, if we take the hydronium, and it can either be H plus or H3O plus, concentration over the total initial concentration of this molecule, which we know is 0.1, that is, and you multiply by 100%, that's going to equal 3.7%. Okay, so what we're going to do then is we're going to try to get this by itself, and the way we do that is, I'll do two steps in one, so I don't want to lose you here. I'm going to divide both sides by 100, so we'll end up with 100 on the bottom over here, and I'm going to multiply both sides by 0.1. So what's going to happen is the 100's going to disappear, the 0.1's going to disappear on the left side, and we're going to just be left with the hydronium concentration. So I'll go ahead and do that. So 0.1 up here, and 100% down here, and then 100% over here on this side, I'm going to have times 0.1 and 100% here. Alright, so this cancels, and now our H3O is going to be the percent signs cancel, so it's going to be 3.7 times 0.1 divided by 100. Okay, and that gives us this, 0.0037. So that's the concentration of hydronium at equilibrium. That's the key. All right, so that means the hydronium down here on the equilibrium line, I can write that number. It also means, since this is a one-to-one relationship, for every lactate acid that breaks up, you end up with one hydronium and one of the conjugate bases here. This is also going to be 0.0037. And this started off as 0, and this started off as 0. So again, this is like a little puzzle. You're just filling in these boxes. That means this has to be plus. Okay, and since we added this much of each of these, that means we had to lose this much of that. We had to use up this much of that. So over here, this is going to be so we'll do that on the calculator. And that gives us okay, so we have all three of our equilibrium concentrations, and in actual numbers, not in x's and variables and so forth. So now we can go ahead and calculate the Ka. So let's write the general equation. It's always good to write the general equation first. So Ka equals Okay, and now we can plug in the numbers. Let's just do it right over here. So it's 0.0037. And then the value of this was, the equilibrium value is that, 0.0963. So that means Ka will simply be the result of that. And that gives us this. And the solution shows that in scientific notation and rounded down to that. So it's 1.4 times 10 to the minus 4. And that's the solution for exercise 14. All right, so we're on to number 15, and it says calculate the pH for a 15 molar solution of NH3. So you should recognize by now, I hope, that that's a base. If you don't, then you have the base dissociation constant there, Kb. So that is a base. So they want you to go from a concentration of a base, which is an OH concentration, that's always what a base has, to a pH. So let's look at the road map, and you can plot several ways to get there. One of them is you start with your OH concentration. That's what they gave you. You can come down here and you can move across to figure out the pOH. And then you can come down here and use this first equation. Remember, these are the translators that get you from bases to acids and from acids to bases. And if you know pOH, then pH plus the pOH will equal 14, so that'll tell you the pH. The other strategy you could have used is go from OH to pH, and you could have done that, from OH concentration to H plus to hydronium concentration, and you could have used the second equation for that. You're given the OH concentration, and you know that that times whatever the hydronium ion concentration is going to equal 10 to the minus 14th, so you could figure out the hydronium ion concentration, and then you come up here, up to the upper left-hand side of the road map here, and you have the hydronium, and if you take the negative log of that, that will give you the pH. So there's several routes to getting there. So we'll go ahead and do that. And it gives you a Kb also. So let's see, that's going to indicate maybe that we're going to need, well, that means to have a Kb to use that, you're going to need to know the ammonia, the ammonium, and the hydroxide concentration. Let's go ahead and write that equation. Okay, so you start with water. This is a base. That means it's going to accept a proton. It accepts it from water. It's a weak base in water, so it doesn't, not all the water molecules break off into that. In fact, there's way more water molecules than ammonia anyway. But one of these is going to go over there, and I'm going to write some H plus will transfer over to the ammonia because it's a weak base, so only some of these will come over. What that does is it turns the water molecule into an OH minus. It lost the hydrogen, but not its electron. The electron stayed behind from this hydrogen, so it's an OH minus. And then that proton came over to NH3 to make it NH4. But again, it was only the proton. It wasn't the electron of the hydrogen as well. It was only the proton of the hydrogen, the positive charge. So it makes that the positively charged ion ammonium. Okay, so let's set up an ice table. Once you got the equation, just go ahead and do this. You never include water, so you could scratch those out. And it tells us that it's 15 molar, so this is a 15. And we assume that this is 0 at the beginning, of course. All right, so now you're going to subtract x. See if you can do this now on your own. Okay, so good. So now we're going to go ahead and write our law of mass action. I'm going to write it in the generic form first. And there it is. Of course, you don't use the water. All right, so let's right over here. Let's plug in do our algebra. So it's x times x. This is the x, and this is the x there. So it's x times x is x squared. And that's going to be over 15 minus x. And that's equal to the number they gave us for the dissociation for the kV. That's 1.8 times 10 to the minus 5. Okay, so again, we're going to use our small variable of approximation. Again, because it's a weak base, not very much of this. This is a lot of ammonia, 15 molar, and only a very small fraction of it is going to dissociate. So we're going to use x is very small compared to 15, so it goes away. And now we can multiply. Let's come on down here. We're going to multiply both sides by 15. I'll just go ahead and do that here. And over here, this is times 15 as well on this side. So we'll come down here. These 15s cancel. So you end up with x squared equals, and 15 times 1.8 is going to be 27 times 10 to the negative 5. So now we simply take the square root of both sides to find out what x is. Remember your keystrokes. Second x squared gives you a square root sign. And it's 27 times 10 caret negative 5 close parenthesis. And that gives you this. And I'm just going to stop it at that. Okay, so what is that? Well, that is the hydroxide concentration. That's this right here. So that means our hydroxide concentration equals this. And you may have your own preference, but my preference is to convert this to POH and then use the simple arithmetic pH plus POH equals 14. So POH equals negative log. Again, go back here if you need it. And there it is up here, right there. We're converting from OH to POH now. So it's negative log of that number, 0.016. And that gives us 1.80 for POH. So now we can use the formula. Again, I urge you to always write out the formulas, the general formulas first before you plug in numbers so that they become natural. That's the general formula that relates pH to POH. So pH plus 1.8 equals 14, and that means pH is going to equal 12.2. Okay, and that's the answer they got. That's the answer they got right there. Okay, all right, so let me leave that on the screen there. Okay, so again, what was the strategy here? They gave us an initial concentration, but it was of a base. So we had to figure out things in terms of the base reaction, come up with our OH concentration, and then we could have converted that to our H plus concentration, or we could have done what I did, which I just like doing better. I convert that to a POH, and then come down and use this formula to figure out what the pH is. And that's it. Okay, these ice tables, again, ice table and the law of mass action for an acid or a base, this equilibrium equation, they go together. They work together to solve these types of problems. So again, you can do, between now and the AP, if you can do 30 of these problems, you'll be the world champ at them, okay? They won't be able to throw anything at you can't do. Okay, so now we're on to exercise 16. Very similar to the last one. They throw a little curve at you here, a little, see if you can handle this. So it's calculate the pH of a 1 molar solution of methylamine, and they give you the Kb. Okay, so we're going to do it the same way as the last one, and we're going to first write the equation for this. So we write H2O plus methylamine, and you sit there and you say, okay, I don't know what methylamine is. So you know what? It doesn't matter. You write the word base. And then you come over here, and the H2O lost a hydrogen because the base accepts a proton. So it lost a hydrogen proton, but it left its electron behind, so it's OH minus. And then that's going to be plus. The base gained that proton, so we're just going to call it base plus. I mean, it really doesn't matter what you call it. So that's all you need to know. So it's ICE. We don't use water in these equations. And it says it's a 1 molar solution of the base of the methylamine, so that's 1. And it's going to be minus X is 1 minus X. You start off with no hydroxide and none of the conjugate acid of that base. And so now you add an X, and you end up with X down here, and you have the Kb. So Kb, again, write the generic equation. It's going to be OH minus times base plus, which is the conjugate acid of that original base, methylamine. And then down here is just base. So that's going to equal, that's X, just like the last problem. It's going to be X squared over 1 minus X equals the dissociation constant, the base dissociation constant, so 4.38 times 10 to the negative 4th. Alright, we can assume that the X will go away. So all we have left is X squared equals that. So we're going to take the square root of both sides. Second, X squared gives you square root 4.38 times 10 caret negative 4 in close parenthesis, and you get this. Okay, so that's X. And what is X? I'm off screen. Sorry. Okay, I'm off screen. So all we did was that X squared. That 1 is just 1, so it's X squared equals that. So you take the square root and you get this number right here. That's X, so it is X. X is our concentration of hydroxide. So we want to get to pH, so I'm going to do it the same way we did last time. POH equals negative log of the hydroxide concentration. And that is going to equal 1.67. So that's POH. So we know that pH plus POH equals 14. So 1.67 equals 14 plus pH. So 14 minus 1.67. And that gives you a pH of 12.3. And that is what they were asking for. And yeah, it's 12.32. That's what I got. So 12.32. All right, that's what they got. And that's the answer to that. Okay, so the only twist here was, what if you don't know what the formula is for that? It doesn't matter. You just call it base. And you just write the formula the same way. All these formulas are the same, okay? For acids, for bases. All the base formulas are the same. All the acid formulas are the same. So, not hard to do. All right, let's keep going. Okay, we're on, there is no exercise 17 here. We're going to move on to exercise 18. So it says calculate the pH of 1 molar sulfuric acid. So what makes sulfuric acid different than the ones we dealt with is it actually has 2 protons in it. The first one is a strong acid. So the first one totally dissociates. The second one is a weak acid, so it only somewhat dissociates. So let's go ahead and write the equation for this. So you have water. Okay, so one of these 2 protons jumped over to the water molecule to turn it into a hydronium, positively charged, and the sulfuric acid, which was electrically neutral, now has a negative charge. It's now a negative ion, and that's sulfurous acid right now. Okay, so this completely dissociates. So when we make our ice table, it looks like this. Don't include water. So you start off with 1 molar, and if it totally dissociates, you end up with none of this left. It's all changed. So you subtract 1 molar, and at the equilibrium, you have none of this. It's no longer sulfuric acid. Now we come over here, we started off with no hydronium, and for every mole of this that dissociated, 1 mole of this was produced, and so that's +1. You don't need any x's here, it's just straight up numbers. And so that means you end at the equilibrium, you ended up with 1 molar. And then the same with this. You have to have the same number of molar of this and this, they're all 1s. So it's also started off with 0. You added 1 molar to this and ended up with 1 molar. So the K, there's 2 dissociation constants for the acid. The first one is for what we just did, having that first hydronium or hydrogen dissociate. And that's very large. Why? Well, let's go ahead and write the law of mass action for this. And it's going to be this. Okay, so this is 1, and this is 1, and this is now 0. So if you do that, you have 1 times 1 is 1 over 0. So as you know from math, you can't have a 0 in the denominator. That's basically undefined. But let's just imagine instead of 0 is just a really tiny number. So then that means 1 over a really tiny number is going to be a really big number. How big? Who knows? Who cares? It's just super big. So what you would then say, the way they write this, is that the dissociation constant for a strong acid is much greater. Those are 2 greater than signs, so it means much greater than 1. Because it's approaching infinity if that number is just a really tiny number. Okay, so that's basically it for that. So what's important here is that the equilibrium concentrations of everything are shown on that bottom line. So you really don't need to make ice tables for strong acids. There's not really a point in it because they totally dissociate, and what was 100% on the reactant side at the beginning is 100% on the product side at the end. Okay, but now what we're going to do is we're going to figure out the dissociation for this. This is what you have now in solution along with this. So we're going to go ahead and write, and that's an H. Let me make it look like an H. That's sulfurous acid. So we're going to go ahead and do a second ice table. So it's H2O plus HSO4 and now since it's lost 2 protons, it's now a 2- charge right there. Alright, let's write ice table. And this, nothing for water. And so what are we starting with here? Well, we're starting with whatever the equilibrium concentration was at the end of the first part of the reaction, which is 1. So we're starting with a 1 here. And now you can't just subtract 1. This is not going to totally dissociate. So it's some unknown X. And now it's kind of looking more familiar to us as an ice table. Over here, the H3O started at 1 because we already had 1 molar from the previous reaction, from the dissociation of the first proton. And now you're going to add X to that, and you have 1 plus X. And finally, this, you didn't have any of this in solution because none of this was produced up here. You didn't have any of this at solution at the beginning, but you do add the X to it, and you end up with X on the bottom. So there you go. And so there's the equilibrium algebraic expressions. So now we are going to write our equilibrium constant expression. And that's going to be H3O. All right, and we'll plug in our variables. And so we have this for the H3O, we have this for the SO4. And then we have this for the HSO4 minus. And that is going to equal the number that they give us back here on the previous page from this table is, let's look at this. For sulfuric acid, it's right there. So the first is large. That's what we just said. It's a number much, much, much greater than 1 because it totally dissociates that first hydrogen, that first hydronium does. The second one is an actual number. It's 1.2 times 10 to the negative 2. So that's the one we're using for this second. That's for the second proton. That's for the second H that you see there. And that's what we're going to use for our Ka. So we're going to go back over to the other page. Get it together here. Give me a second. Alright, so we're down here. So that means the KB, I put KB, it should be Ka. Alright, so that's going to equal, up here I'll write it. We said from the previous page it's 1.2 times 10 to the negative 2 from that table. Alright, so that's what that's going to look like. Now we got a little algebra to do. Since this is a fairly large number, it's not a negative 5 or negative 8 or negative 10, you can't use the small variable approximation. So you are going to have to use the quadratic formula. It won't kill us to do it one time. So let's just practice it. They won't ask you to do it on the AP, but it's just a little math practice here. So here we go. I'm going to write this again. Alright, and so what you're going to do is multiply both sides by this 1 minus x. And it's going to cancel there, and over here is 1 minus x. Okay. And so if you multiply this through, you end up with 1.2 times 10. Since that's a fairly large number, it's not a lot of zeros in front, I'm going to just call it what it is in normal decimal numbers. So you move the decimal over 2 places to the left, and it's 0.012. So I multiply that through, I distribute that here, and then I have 0.012. Again, that's what this is equal to as a regular decimal number, x, because I multiplied it by that right there. Okay, let's not get our time sign confused with the x. That's an x right there. All right, on the other side, what you have is x times x is x squared, and x times 1 is plus x. So you can see we're forming a quadratic here. All right, if I add this to both sides, and add this to both sides, okay, so that's going to come over here. So I'm going to add 0.012x there, and over here I'm going to add 0.012. Then the equation I end up with down here is x squared plus, this is a coefficient of 1, so 1 plus this is going to be 1.012. Just 1 plus that. That's x. And then there's nothing up there, so it's plus 0.012. And on the other side, you now have 0. You've moved everything away from that. So now you have it in a form where you could find the roots either by factoring or by the quadratic formula or whatever. And the quadratic formula is always the best way to find roots, because they will find irrational roots for you, whereas factoring won't always do that. And it's just easier to plug numbers into a formula. I'm going to violate my rule. I'm not going to write out the quadratic formula. I'm just going to go ahead and plug in the numbers here. So what we have to say is that a in the quadratic formula is equal to 1. That's the coefficient right here. B is equal to 1.012. That's the coefficient here. And C is equal to 0.012. Okay, and our solutions x are going to equal, I'll just say the quadratic formula, it's minus b plus or minus the square root of b squared minus 4 times a is 1 times c is 0.012, and that's all over 2 times a, 2 times 1, which is 2. And what you'll end up with is two solutions. X equals, okay, so as I went to do the calculation, I realized I had made an error. I was supposed to subtract minus 0.012. So over here it would have been minus 0.012. That would have made that a minus, and that would have made my C value negative 0.012. So I went ahead and corrected that. I'm not asking you to get bogged down in this calculation, but the values of X that you come up with, because remember in quadratics you can come up with two values, what are called two solutions or roots. One of them is positive, one of them is negative. Well, since this represents a concentration of a substance, it can't be a negative number. There's no such thing as a negative concentration. So you can eliminate this one. So this would be your answer. Now, if you go back up here and look at the equation we originally had right here, if we had used the small variable approximation and gotten rid of this x because we assumed it's small and this x, you would have simply had on this side 1 times x over 1, which is x, equals that exact same number, 0.012. So either way, whether we use the quadratic or the small approximation, it would have given us the same answer. so that is the concentration then of the SO4. It's right there, so this is what X equals, 0, 1, 2. So that's the concentration here. If you want the concentration of the hydronium ion, the H3O plus, it should be, then it's 1 plus that number, so that's 1.024. All right, so that's the concentration of that. So if you want to know the pH, you have to take the negative log of that number. Negative log, so down here we'll write it. Of the hydronium, which in this case, I'll just go ahead and write it straight up here, is 1.0, and I wrote 2 for it. I don't know why. It should be 1.2. 1.012. In other words, it's the same as this X, except you add the 1 to it. So it's 1.012. Okay. And that would give us a pH, which is what the question was ultimately asking for. I'll calculate that. Keep my paper from falling off here. It gives us a pH of negative 0.005. Effectively, it's 0. So we're just going to call it a pH of 0. Okay, and that is the final answer. All right, that's a little messy, but you could have used the small approximation and avoided all this. They will, as I've said many times, will not ask you to do a quadratic on the AP exam. All right, and I'm going to call that a video here. It's 58 minutes. Remember, we're working these problems. I'd like you to work as many of these as you can this weekend. The more you can get out of the way this weekend, the fewer you have to do during the week. But I'm asking that you try to get through number 15 at least. So we're up to 18. And I'm going to continue to record these videos this weekend in case you want to try to do the entire assignment. I will be in Monday from 9 to 12. And you can come in for tutoring if you would like. Some of these are challenging problems, but these are AP level problems that you're doing here. Okay, so I'll see you on the next video.